Okay, so let me see. Um, C++. Yeah. Okay, we will go to basics and okay, const qualifier. Okay, now I'm here for const expression and expr and constant expressions. A constant expression is an expression whose value cannot change and that can be evaluated at compile time. A literal is a constant expression. A const object that is initialized from a constant expression is also a constant expression. As we'll see, as we'll see, there are several contexts. As we'll see, there are several contexts in the language that require constant expressions. Whether a given object or expression is a constant expression depends on the types and initializers. Okay, so constant expression is a constant expression. Max files. Okay, staff is not a constant expression. Kit size is not a constant expression. Okay. Although staff size is initialized from a literal, it is not a constant expression because it is a plain int, not a const int. On the other hand, even though sset is a const, the value of its initializer is not known until runtime. Hence, okay, so they should be evaluated at compile time. Hence, sset is not a constant expression. Okay. Then const expr variables. In a large system, it can be difficult to determine for certain that an initializer is a constant expression. We might define const variable with an initializer that we think is a constant expression. However, when we use that variable in a context that requires a constant expression, we may discover that the initializer was not a constant expression. In general, the definition of an object and its use in a such context can be widely separated. Okay. Under the new standard, we can ask the compiler to verify that a variable is a constant expression by declaring the variable in a const expr declaration. Okay. The variable declared as const expr are implicitly const and must be initialized by constant expressions. Okay. So, okay, if this is a const expr function. Although we cannot although we cannot use an ordinary function as an initializer of const expr variable, that the new standard lets us define certain functions as const expr. Such function must be simple enough that the compiler can evaluate them at compile time. We can use const expr function as an initializer of const variables. Generally, it is a good idea to use const expr for variable that you intend to use as constant expressions. Literal types. Because a constant expression because a constant expression is one that can be evaluated at compile time, there are limits on the types that we can use in a const expr declaration. The types we can use in a const expr are known as literal types because they are simple enough to have literal values. Literal types, simple enough to have literal values. Of the types we have used so far, the arithmetic reference and pointer types are literal types. Our sales item class and library and IO are not literal types. Okay, so type we have used for arithmetic reference and pointer types are literal types. Okay, these are literals. Hence, hence we cannot define variables of these type as const xpr. Okay, we'll see other literal types in 7th chapter. Although we can define both pointers and reference as cont expr, the objects we use to initialize them are strictly limited. We can initialize a const expr pointer from the null pointer literal or the literal, that is constant expression 0. We can also point to or bind an object that remains at a fixed address, okay, that is static. For reasons we'll cover in, variables defined inside a function ordinarily are not stored at fixed addresses. Hence, we cannot use const expr pointer to point such variables. On the other hand, the address of an object defined outside any function is a constant expression, and so may be used to initialize a const expr. Okay. That functions may define variables that exist across calls to that function. Like an object defined outside any function, these special local objects also have fixed addresses. Therefore, a const reference may be bound to such variables. Okay, static objects, I think, static variables. Pointers and const expr. It is important to understand that when we define a pointer in a const expr declaration, the const expr specifier applies to the pointer, not the type to which the pointer points. Okay, const pointer to int. The pointer. Okay. This is important. The pointer to a constant, but this is a const pointer. Despite appearances, the type of P and Q are quite different. Yeah, right. P is a pointer to a const, whereas Q is a constant pointer. The difference is a consequence of the fact that const expression impose top level const on the object it defines. Like any other constant pointer, a const expr pointer may point to a const or a non-const type. Okay. PNLPR cont expr int. Okay. So int j, P is a constant pointer to int j, const. Okay, it is the type doesn't matter here, right? Because it is a const pointer and it can bind to. Okay, is the following code legal or not? If not, how? Okay, int null equals to 0. Okay, because int, no, you cannot, as it matter, value is 0, you cannot assign. If its value is 0, no, it doesn't matter. You cannot assign a variable value to initialize a pointer. It has to be a literal. Okay, then we move on to dealing with types. As the programs get more complicated, we'll see that the types we use also get more complicated. Complications in using types arise in two different ways. Some types are hard to spell. That is, they have forms that are tedious and error-prone to write. Moreover, the form of a complicated type can obscure its purpose or meaning. The other source of complication is that sometimes it is hard to determine the exact type we need. Okay. Doing so can require us to look back into the context of the document. Type aliases. The type alias is a name that is a synonym for another type. Type aliases let us simplify complicated type definitions, making those types easier to use. Type aliases also let us emphasize the purpose for which the type is used. Right. We can define it. Traditionally, we use a type def. The type def keyword may appear as a part of the base type of a declaration. Declarations that include typedef define type aliases rather than variables. Okay. As in any other declaration, the declarators can include type modifiers that define compound type built from the base type of the definition. Okay, I didn't get it. Okay. We can define type aliases in one of two ways. Traditionally, we use typedef. Right. Typedef wages base and okay. Base is synonym for double and p for double pointer. Hmm. Okay, alias. So it basically uses this in place of this. Okay. Alias works by substituting the base type in place of the new alias is defined. Right. The keyword typedef the keyword typedef may appear as part of the base type of a declaration. Declarations that include typedef define type aliases rather than variables. As in any other declaration, the declarators can include type modifiers. Okay, type modifier like that define compound types from the base type of the definition. Right. Okay, so pointers and all. The new standard introduced a second way to define type alias via alias declaration. Okay. An alias declaration starts with the keyword using followed by the alias name and an equal to. SI is synonym for save item. The alias declaration defines the name on the left hand of the equal to as an alias for the type that appears on the right hand side. A type alias is a type name and can appear wherever a type alias is a type name and can appear wherever a type name can appear. Okay. Pointers, const and type aliases. Declarations. Here is a PS is a pointer to a constant pointer to char. Okay, so it is a p string is a pointer of type char, and we call this a pointer to a char as p string. Okay. Pointers, const and type aliases. Declarations that use type aliases that represent compound types and const can yield surprising result. For example, the following declaration uses the type p string, which is an alias for type char star. Right. Okay. So p string is a type for char star. So const p string c star is a const pointer. Is a constant. Is a constant pointer. Right. Okay. Pointer to a constant pointer to char. Okay, because uh, const cstr is being defined as const star const char star cstr. So is it a constant pointer? CSTR is a pointer. It's a pointer is a pointer, is a const pointer. Oh, wrong embedded. Okay. Right, okay, so I should just wait. Okay, CSTR is a constant pointer, not a point. Okay. The pointer to a constant pointer to. The base type in this declaration is const pstring. As usual, right? Pstring, because pstring itself is a pointer. As usual, a const that appears in the base type modifier modifies the given type. The type of pstring is a pointer to char. So const pstring is a pointer to char, constant pointer to char, not a pointer to const char. Okay. It can be tempting, albeit incorrect, to interpret a declaration that uses type alias by conceptually replacing the alias with its corresponding type. Right. However, this interpretation is wrong. This interpretation is wrong. Okay. When we use pstring in a declaration, the base type of the declaration is a pointer type. Okay. When we rewrite the declaration using char star, the base type is char, and the pointer part, the base type is char, and star is a part of declarator. In this case, const char is the base type. This rewrite declares C star as a pointer to const rather than a const pointer to char. Okay. The base type of the declaration is a pointer type. Okay, so it is a pointer by default. Right. Base type is pointer. Declaration is okay, so it becomes a const pointer, not a pointer to a const. When we rewrite the declaration using char star, the base type is char, and the star part is of the part declarator. Okay. Okay, so it is saying that that this is a P string has a base type char star, which is a pointer, and if we apply const to a pointer, we get a const pointer. But if we interpret as const char star cstr, here the base type is const char and becomes part of the declarator. Declarator is out of the wait. Declarator of the declarator and not the base type. Hence, CSTR is a pointer to const char, but that would be wrong to interpret as. Let me just go it. Yeah, okay. Can I? Okay, I cannot. Put as. Okay. Okay, the auto type specifier. It is not uncommon to want to store the value of an expression in a variable. To declare the variable, we know we have to know the type of that expression. Okay, when we write a program, it can be surprisingly difficult and sometimes even impossible to determine the type of an expression. Under the new standard, we can let the compiler figure out the type for us by using auto type specifier. It is not a good practice, I think. Like type specifier, like such as double, that name a specific type. Auto tells the compiler to reduce the type from the initializer. By implication, a variable that uses auto as its type specifier must have an initializer. Okay, it must be initialized, right? You cannot leave. Here the compiler will reduce the type of item from the type returned by applying item will have the type sales item. If those variables are type double, then item has the type double and so on. Okay. As with any other type specifier, we can define multiple variables. We can define multiple variables using auto because a declaration can involve only a single base type. The initializer for all the variables in the declaration must have the same type that are consistent. Okay. So this is wrong. Right. That is right. We can define multiple variables using auto because with other. Okay. Compound types const and auto. Okay. A is an int, R is an alias for I, which is a type int. Okay, right. The type that the compiler infers for auto is not always exactly the same as the initializer type. Instead, the compiler adjusts the type to conform to normal initialization rules. First, as we've seen, when we use a reference, we are rarely using the object to which the reference refers. In particular, when we use a reference as an initializer, the initializer is the corresponding object. The compiler uses the object's type for the auto's type deduction. Okay. Second, auto ordinarily ignores top level const. As usual, in initialization, low level const such as when initializer is a pointer to const are kept. Okay. So const int ci, and this is a reference to type const constant. So auto b ci, this is a constant. Top level const is ci is drop ci. Okay, b is an int. Okay, this is top level. Isn't this lower level const? What is c equals cr? C is an int. Okay, then we go. Okay, top level const. Okay, low level are kept. Okay, low level close to the. Okay, got it. So it will drop auto b. It will drop this. This is top level const. So this is int c cr. Okay, the type of cr base type is constant. The const. Okay, so CCR base type is constant, but type modifiers are not included. Okay, then top level constant is dropped, so this is int. End of AI. Okay, address. So this is a pointer. Constant is declared the int pointer, and end of CI to CI. Okay, so CI. Low level const such as when an initializer is a pointer to const are kept. Const int and of a const object is Okay, address of a const object. Okay, because type is important here. Okay, right. The base type is important in this case. Oh, because it no. If we want the deduced type to have a top level const, we must say so explicitly. Okay. We can also specify that we want a reference to auto deduced type. Normal initialization rules apply. Okay, so this is a constant reference bound to CI. We can't find a plain reference to a literal. Const object, okay, you can find a const to a literal. We can also specify that we want a reference to the auto deduced type. Okay, right. Const auto reference to because it binds to a temporary variable. Okay. When we ask for a reference to an auto deduced type, top level consts in the initializers are not ignored. As usual, consts are not top level when we bind a reference to an consts are not top level we bind a reference to an initializer. Um, When we define several variables in the same statement, it is important to remember that a reference or pointer is part of the particular declarator and not part of the base type of the declaration. Okay, so auto k equals ci. Okay, what is ci? Ci is a constant. Okay, constant. So k is int. Okay, and L is simple reference to int. Auto mci. Okay, this is a constant reference and pointer to ci constant, so it will be a const int pointer to constant. Error type deduced auto n equals I. Deduced I is int and it cannot be a pointer to a right. Okay. Using the variable definitions from this section, determine what happens in each case. Okay. Assignment A. Let me see where is A. Okay, A is auto A is R int. Okay. So this is okay. B. What is B? B auto B CI. So this top level const is dropped. B is a int. So this is also okay. Then we move on to C. CR. CR is a reference. Okay, C is a reference to CR. C. Okay. And CR has the type const int to CI. Okay, so CR is an int. CR is an alias for. Okay, so we drop this. C is an int, right? Okay, so yeah, okay, C is an int, so this is also correct. Then move on to D. D has the address, so it is a pointer, int star pointer. Okay, that is okay, you can do that. E. Okay, now when we define a pointer to a const, the top level const is it what is it, are kept, right? So const we cannot change. Well, no, we can change. Since e is a pointer to const but not a const pointer, it's the address it points to can be changed. Okay, so I guess I will just put it over here. Okay, then G, where is G? F G. Okay, to G C I, it is a reference. So when we go with we define reference, so the top level constant, so it is a constant reference. Okay. It is a reference to a constant. G is a constant reference that is bound to CI. Constant reference. Okay. Since G is a constant reference, we cannot change the underlying value of the constant object, variable. Okay, great. Write a program containing the variables and assignments from the previous exercise. Print the variables before and after the assignment to check whether you're okay. Write a program containing the variables and assignments from the previous exercise. Okay, so we will quickly do that. Variables and basic data types. I want to auto specifier. Auto reference end at the end pointer. Yeah, okay. HTML. Go to exercises. This is exercise 2.5.2. Exercise 2.5.2. I create a new file. Called main.cpp. .cpp to main.cpp. And okay. So let's go and define here auto I equals 0. So this will deduce, and p is a pointer to I is an int, and p is a pointer to int, right? Okay, I think int I, sorry. So that's okay. We'll go with int I equals 0 and we define a reference to I. And then we have auto a equals r. The type modifier is dropped and it only takes into account the paste type. Hence a is an int, right? Then we have constant ci. constant ci equals I and cr equals cr. Okay. And it is a const reference. Okay. Ci is a constant and cr is a constant reference, right? Then we have auto b equals ci, auto b equals ci, top level const are stopped unless specified explicitly, hence b is int, right? Okay, auto c equals cr, auto c equals cr. Okay, again same happens and c is an int. Then auto d equals end of I. Okay, d is a pointer to int. Then we have auto e equals end of cr. Okay, now in this case, as only const, the const int pointer, right, okay. Point to const objects, hence const is important in this case, hence e is of a constant. Okay, then we have const auto fci, const auto f equals ci. Now the const is explicitly defined, hence the type of f is constant. To specify that we want the reference to the auto deduced type. Okay. Const auto and g equals ci, right? So now since we have explicitly defined const with friends, hence the type of g is constant reference. Okay, auto g okay, so const auto and h equals 42, right? Literal. Okay, since the base type of 42 is int, plain reference to a literal. Okay, sorry, constant auto reference h equals 42. This will throw an error as we cannot bind plain reference to a literal. Then we have const auto and I equals j equals 42. As we've studied, it binds to a temp object. K and all are not. Okay, so test A equals 42, B equals 42, C equals 42, then D equals 42, then E equals 42, and then finally G equals 40. Let me try and do this. Make main should right. Okay. Invalid conversion from int to int star. Okay, invalid conversion. Int. Okay. Okay, so I am wrong here. This. Okay. Cannot point to a literal, has to be a valid object. D, E can't point to a literal, has to be a valid address in memory. Right. Okay. Okay. Determine the types reduced in each of the following definition. Once you've figured out the types, write a program to see whether you were correct. Okay. So let's see, const int I. Okay, auto j equals I. Let me try and write I is int, right? Const auto and k. Okay, since it adds a const and a reference, we say it is a const reference. Okay, k equals const int reference. Const references can point to const as well as non-const objects, right? I hope so, if I'm not wrong. Then auto p p is int star, int pointer. Then const auto j. Okay, so j2 is const int. And it says a const reference to I. K2 const int reference, right? Yeah, let me 2.3.4 2.3.4 clear. Okay, so 2.3.4, then this is 2.3.5, 2.3.5 nahi 2.35, 2.34 and I 2.35.cpp. okay, no, can get tricky. Okay, let me see, const int I equals 42, then we have auto j equals I, definitely, and since top level const is dropped, right, then we have const auto auto and k equals I. uh, K is constant reference which can bind to both const and non-const types. Then we have star p equals address of I. P is integer pointer. const auto j2 equals I. Const auto j2 equals I. So j2 is constant. Okay. And we have a auto and and k2 equals I. And k2 is constant reference like 2.35. Yeah. Okay, so how can I print the type of the variables in C++? Type info, right? Type id dot name. Okay. For let's print the types of the variables. What is this? Type id I dot name, right? Okay, we have 1 2 3 4 5 6. 2 3 4 5 6. You get I, you get J, and we have P, and we have, okay, first there was after J, K, then P, then J2, then K2. Okay, so clear 2.35. Okay, this might be a problem. 2.35. Okay, G++ 2.35 dots dash main. I don't get name, type ID, select data type, type info, type ID, name. Type name. Okay, wait, I can deduce from the type of operations they can do, right? Okay, so if j is I can assign j value of, say, 32, right? and let's say since j is int, so let me value of j j set 0. Okay, const onto, it's a const int reference. Okay, what can const int okay, const int references by default okay, k equals 20. Value of k slash I is k clear. Okay, assignment read only. Yeah, right. Because since k is a constant reference, it can only be used to read the value. However, the value of the underlying object can change regardless, right? So this is invalid. So it's constant. Okay, it can point. Okay, then we have value of p equals let's say 50. Then here value of slash I dereference operator, read only. Oh, sorry, int pointer. Okay, constant. Alright. Hold up. Assignment. Since okay, assignment of read only reference k, assignment of read only location star p. Okay, so apparently you can point to a read only location, but you cannot change it. Okay. Since I is constant, it is by default read only and cannot be changed. Okay. Const auto int j2 equals 50. Since j2 is constant, its value cannot change. Value j2 slash I it will throw me an error. Read only variable, and then k2 is a read only reference. Read only reference that is it is a read-only reference, that is constant. Yeah. That's wrong. Value of key slash I. Hmm. Hmm. Shit. Hmm. Okay, now we move on to declare type. The declare type specifier. Sometimes we want to define a variable with a type that the compiler deduces from an expression, but do not want to use that expression to initialize the variable. Okay. For such cases, the new standard is introduced, a second type specified declare type, which returns the type of its operand. Okay, declare type. Okay. The compiler analyzes the expression and determines its type but does not evaluate the expression. Right. Nice. Okay. Here the compiler does not call f, but it uses the type that such a call would return as the type of sum. That is, the compiler gives sum the type as that would be returned if we were to call f. The declare type handles top level const and references differ. The declare type handles top level const and references differ certainly from the way auto does. When the expression to which we apply declare type is a variable, declare type returns a type of that variable, including top level const and references. Declare type returns a type of that variable, including and references. Okay, so constant ci constant, cj constant reference, and is bound to x. Constant reference, but error. Reference must be initialized, right? Yeah, because cj is a reference, declare type cj is a reference type. Like any other reference, must be initialized. It is worth noting that declare type is the only context in which a variable defined as a reference is not treated as a synonym for the object to which it refers. Declare type is the only context in which a variable defined as a reference is not treated as a synonym for the object. Okay, let me create auto specifier. Let me give it 11. Then this is 12. Tackle type. cd2 10 exercises. Then why does it show that cd is invalid? Okay, declare type. Oh, my bad. Clear. Okay, let me make a new file, declare type.cpp, and Tickle type reduces the type of its operand, including top level consts and references. Okay, so let's say constant ci equals 0 and constant reference cj is equals to ci. I say tickle type ci of x equals 0, so ci is constant. Then we have tickle tickle type cj, okay, cj y equals x, right? Cj is constant reference, right? Tickle type and references, and we move on to defining our own structure. Struct cell. Okay, let me just finish tickle type, right? Should finish tickle type. Tickle type cj z. Tickle type cj z error as like any reference must be initialized. Tickle type and references. When we apply tickle type to an expression that is not a variable, we get the type that the expression yields. Okay, we get the type that the expression yields. As we've seen before, some expressions will cause tickle type to yield a reference type. Generally speaking, tickle type returns a reference type for expression that yield objects that can stand on the left hand side of the assignment. Okay, assignment. Generally speaking, tickle type returns a reference for expressions that yield objects that can stand on the left hand side of the operand. Okay, so int I reference. So tickle type of an expression can be reference type. Okay, so C is an int reference. Okay, C, I don't know where is C defined. C is not defined. Here is an int. B is an uninitialized int. C is an int reference and must be initialized. I don't know. Okay, here R is a reference to, so tickle type R is a reference type. Okay, R is a reference, so tickle type R is a reference type. If we want the type which R, okay, R is a reference, so its type will be reference. Right, this is correct. Okay, reference type. If we want the type to which R, if we want the type to which R refers, we can use R in an expression such that R plus 0, which is an expression that yields a value, as a non-reference type. Okay. On the other hand, the dereference operator is an example of an expression for which returns a reference. Okay, so it is a by design. As we've seen, when we dereference a pointer, we get the object to which the pointer points. Moreover, we can assign that object. Thus, the type deduced by tickle type pointer is not plain int. Okay. Another important difference between tickle type and auto is that deduction done by tickle type depends on the form of its given expression. What can be confusing is that enclosing the name of a variable in parentheses affects that type returned. When we apply tickle type to a variable without any parentheses, we get the type of that variable. If we wrap the variable's name in one or more set of parentheses, the compiler will evaluate the operand as an expression. The variable is an expression that can be on the left hand side of the left hand side on the a variable is an expression that can be the left hand side of an assignment. As a result, table type on such expression yields a reference. Bro, this is plain. Okay. Remember, table type variable, not double parentheses, is always a reference type, but table type variable is a reference type only if a variable is a reference. Hello. Okay, in the following code determine, maybe I'll do it later.